Okay, hey guys, we are on the last section of Chapter 6. Hopefully we have spent enough time on in-class activities and so on for you to catch what's been going on in this chapter. We're on our last video here, and I think most of this is fairly straightforward, but we'll see here. It starts out with what's called the triangle proportionality theorem. And you need to think back to, when do we have that? Chapter 5, right, with the mid-segment theorem, where we kind of split the triangle in half in a way. And we had a mid-segment go from midpoint to midpoint, and that mid-segment was half the length of the third side. Well, this is pretty similar to that, just maybe in a different ratio is all, maybe not 1 to 2. So this theorem says if a line is parallel, which remember the mid-segment was, parallel and intersects two sides of a triangle, it could be anywhere though, intersecting those other two sides. It does not have to be the midpoints now. Then the sides are proportional. So in other words, if we have a diagram like this one, that top yellow triangle compared to the kind of the brownish orange triangle at the bottom, as long as the bottom of the yellow triangle, that top triangle inside there, as long as the bottom of that is parallel to the bottom of the big triangle, then the sides have to be proportional. And so you just have to figure out what that proportion is. And so we could set up a proportion here with, well, just another comparison here. We had an example kind of like this in the last video, and we don't have to take the full length of the side now. Now we're just taking the pieces of the side. And so the proportion that we could set up here is 8 is to y, so the top essentially of the side to the bottom of the side, the left side, is equal to the top of the right side to the bottom of the right side. So we're just setting up a proportion in that way. 8 is to y as 7 is to 3. And there's our proportion, and we would just cross multiply to solve that, and so we would end up with 7y equaling 24, and so if we divide both sides by 7, we'll get 24/7 as the value of y. Now I realize that's a fraction and so on. It would end up coming out to 3 3/7, which again is a fractional component to that, but that's what it ends up being. And so that's the ratio of the sides of those two triangles that are set up there. And the converse of this theorem works as well. If the sides are in proportion, then that means that those bottoms of those triangles have to be parallel to each other. So it works both ways here. It's a biconditional statement essentially. Okay? And so we'll do some practice on this in class and see if that makes sense with a few more examples there. So anything else to add there?
When I look at this, I look at it as, instead of on the previous section we were looking at the differences between the two triangles and finding the similarity between the two, and for this one I just look at it as that one missing piece of one big triangle, I guess, when I look at it.
Yeah.
You know, and maybe that'd be a way to help you guys kind of remember the difference between the proportionality theorem and then the side angle side or side ratios.
Yeah. Yeah. Okay.
All right, so guys, if we have three parallel lines that intersect two transversals, then they divide the transversals proportionally. So it's a lot of big words there for you guys, but don't get scared. All right, I know you can handle it. But basically what it says is, if you look at this diagram here where we have the three parallel lines and they're being cut by transversal L and transversal M, okay, what it's saying here is we can make some proportions out of that, basically between the transversal L and with the transversal underneath it, M. So let me just get to the math because it'll make it easier to visualize when we get to that. But if we take 160 and we set up a ratio with 100, okay, and then we set that equal to 260 over an x, okay, notice that the 160 is being compared with the 100, which is underneath it, and the 200 is being compared with the x, which we don't have underneath that. Now, big thing to pay attention to here is there's an x in the diagram and there's an x in that formula right there. Guys, the x in the diagram is point x, and the x in the equation is variable x. So you just kind of have to visualize that in your head right now, but the 200 goes with that x that's not there, and so all we have to do is cross multiply now, so we get 160 equals, what is that, 20,000? Yeah. And so then you cross multiply, do all your math, divide, and you get xz is 125. Okay? So we'll spend more time with this one in class, but like I said, it's really very simple to see. Just look for where you can make a comparison, and that's probably the right spot to pick it out, and go from there. I mean, Kevin, you got?
Yeah, you're just picking up the pieces of the transversals that the parallel lines cut, and so you just got to think about it that the parallel lines are slicing the transversals, and you're just picking up the slices and comparing them to each other. we're comparing the slices of transversal L, 160 to 200, and we're picking up the slices of transversal M, the 100 to the variable x. It's not in the diagram there, but the variable x, and comparing those in a proportion, and they are proportional to each other as long as those lines are parallel. So, all right. Again, we'll do some more examples of that in class, and hopefully that may make more sense with those examples then. Last slide today is just an example of using the triangle proportionality theorem here. And so we actually have multiple triangles set up in this diagram, and we're trying to find x. And so we can set up a proportion here comparing the pieces of each side. And so if we set up a proportion to where we have the 2x plus 1, which is kind of that middle band right there, and compare that to the bottom piece. So basically what we're doing is comparing the middle piece to the bottom piece, okay, on the left-hand side, and then picking up the middle piece and the bottom piece on the right-hand side and putting those in a proportion. So 2x plus 1 compares to 2x, just as 7.5 compares to 6. And so a little more algebra involved in this one because of that 2x plus 1 in there, but just cross-multiply to be able to come up with that. And so we get 12x plus 6 on the one side. Make sure you distribute through there. And then 2 times the 7.5 will give you 15x on the other side. If we subtract 12x from both sides and divide by the 3 that's left over, then we get x is equal to 2. And so the main key to this, of course, is being able to set up the original proportion. So as long as you can see that proportion is set up from middle side to bottom side on the left, middle part to bottom part on the right side, then the rest is just algebra, just solving the proportion just like we were in the last video that we talked about. So actually from section 1 we've been working on proportions now in this chapter. So as long as you can set up the proportion correctly, you should be able to solve it. So that's chapter 6. And so we'll spend some more time on looking at some activities like this in class and solving some more proportions, but that's the chapter. It's a wrap. So okay,
Here
see
we go.
you guys in class.